Welcome to this explainer. Okay, today we're mapping out the ultimate concept building ladder to help you completely crush Chapter 1, Relations and Functions. Look, if you're gearing up for your 12th board exams, you probably already know that this single topic basically sets the stage for almost everything that follows in calculus and algebra. So we're going to build this up step by step using clear visual rules to really lock these concepts into your memory. Let's get into it.
So, it all comes down to constraints. What actually separates a simple relation from a true mathematical function? Honestly, every student gets these two jumbled up at some point. Why is one a relation and another a function? What are the actual rules? Well, by the end of our time today, the boundary between these two concepts is going to be incredibly sharp in your mind. Here is our agenda for today. Number 1, the mathematical foundation. Number 2, mastering equivalence relations. Number 3, classifying mathematical functions. And number 4, composite and inverse functions.
Okay, starting with Section 1, the mathematical foundation. We are starting with the absolute basics here.
Right, so everything begins with the Cartesian product. I want you to think of this as the grand universe of all possible connections. A cross B is the set of all ordered pairs A, B. Now, the absolutely critical word here is ordered, because order matters. You got to remember that A cross B is generally not equal to B cross A. Think about it. If set A has 3 elements and set B has 4, their Cartesian product will have exactly 12 unique ordered pairings. This is your raw material. But before we add our first rule to that raw material, you absolutely have to know these rapid-fire vocabulary terms. You're going to see these on your exam constantly. The domain is your set of inputs. The codomain? That's the entire universe of potential outputs, but the range is different. That consists only of the actual mapped outputs, the targets that actually got hit, you know? When an input maps to an output, that output is called the image, and the original input is its pre-image. Definitely keep these terms locked in your mind.
Moving right along to Section 2, mastering equivalence relations. This one is a massive board exam favorite.
Board examiners absolutely love to test your logical rigor on this stuff. By slapping a constraint on things, we move from that massive universal Cartesian product down to a relation. A relation is really just a specific subset of those original basic pairings. We don't need all the pairs anymore, just the ones that follow whatever specific rule we set. And within this, you get these special extremes, right? Like the void relation where literally no pairs work, the universal relation where every single pair works, and the identity relation where every element only relates exactly to itself.
Now, board exams love to ask you to prove these, and let me tell you, losing marks on a simple transitive proof is a rite of passage we are definitely going to avoid today. Here's the breakdown. A relation is reflexive if every element relates to itself. It's symmetric if a two-way street exists, meaning if A relates to B, then B absolutely must relate to A. And it's transitive if A relates to B and B relates to C, well, that forces A to relate to C. If a relation perfectly satisfies all 3 of these conditions, it earns the very prestigious title of an equivalence relation. All right, Section 3, classifying mathematical functions. We are adding the ultimate constraint now. Here's the big takeaway, the crucial point. A function is really just a relation, but it comes with a strict, non-negotiable rule. Every single element of set A must have exactly 1 image in set B. You cannot have one input pointing to 2 different outputs. It literally breaks the machine. Every input gets 1 and only 1 output. This concept right here is the bedrock of calculus. Now, when we classify these functions, they exist in mutually exclusive pairs based on how they handle inputs. On one side, we've got 1-1 functions, technically known as injective. This just means every single input goes to a completely unique, distinct output. No sharing allowed whatsoever. On the flip side, we have many-1 functions, where multiple different inputs map to the exact same output. Think about squaring numbers, right? Both 2 and -2 map to +4. That is a classic many-1 function. And similarly, if we look from the perspective of the outputs, a function pairs off into another category. It's either onto, which is known as surjective, meaning the entire codomain gets used up and every potential output is an actual range value, or it's into, leaving some of those targets completely unhit. In that case, the codomain is larger than the actual range. Which brings us to Section 4, composite and inverse functions, the final level of the ladder. Composite functions, denoted as f of g of x, act like a literal mathematical assembly line. You drop your raw material, x, into the first machine, g. It processes it and spits out an output,
But that output doesn't just stop there. It's directly passed as the immediate input into the second machine, F. It's a total chain reaction. And trust me, mastering this chaining concept is absolutely vital for the chain rule and differentiation later on. But wait, what if we want to run that assembly line backward? Well, that's an inverse function. If you see a long answer board question asking you to prove an inverse exists, you want to execute this exact three-step procedure. Step 1, prove it's injective. Step 2, prove it's surjective. Step 3, conclude that because it's both, it is a bijective function. An inverse can only ever exist for strictly bijective functions. If two inputs go to one output, you just can't trace it backward. It's got to be a perfect one-to-one, fully mapped relationship. Oh, and here's a super quick visual pro tip for you graphical learners out there. If you graph a function and its inverse on a coordinate plane, they will always mirror each other perfectly across the diagonal line y equals x. The x and y coordinates literally just swap places. It's such a beautiful visual confirmation of the algebra you just spent time solving. All right, before we completely wrap up, I really want you to commit this rapid review cheat sheet to memory. You're going to need to instantly recognize these standard functions: the modulus function, creating that classic V-shaped graph, the signum function, and pay special attention to the symmetry rules here. Even functions, where f of x equals f of negative x, will perfectly mirror across the y-axis. Odd functions, where f of negative x equals negative f of x, feature rotational symmetry right around the origin. And finally, periodic functions that just repeat their values over a fundamental period t. So we've built an incredibly strong ladder of functions for real numbers today. You've seen exactly how constraints turn chaotic pairings into predictable, reversible, mathematical engines. But as you review these notes for your board exams, I want you to ask yourself, how might these exact same mathematical building blocks evolve when you break out of simple real numbers and finally reach advanced calculus or even complex dimensions? Keep that curiosity alive, go out there and crush those board exams, and hey, thank you so much for joining me on this explainer.